or a cut above. They can split a single hair or a head of lettuce, lacerate entire trees in the blink of an eye, carve through hard steel, or etch it with delicate precision, chopping, slicing, cutting, or biting. Watch your fingers. Now, the world's sharpest on Modern Marvels. What is the world's sharpest? Is it the finest edge? Is it the ease by which one material can slice or puncture another? Or is it something that won't dull with repeated use? The answer, of course, depends on what needs to be cut. This gracefully curved sword is called the katana. It rose to distinction in 16th century feudal Japan, wielded by the legendary samurai warriors. They alone were permitted to carry the katana, and its mystique grew during an era of civil war, as they used it to decimate and dismember their enemies. It is renowned as the world's sharpest weapon for slicing through human flesh and bone. This tough-as-bone bamboo shoot proves too difficult to cut through in a single swipe for a hatchet. Or a machete. But one swing by the katana blade unerringly severs the shoot. Or even two at once. These 5-inch thick woven mats are said to be as tough to cut through as a human leg. But this sword, designed to slice through a torso from collarbone to hip in a single swipe, severs them easily.
Sharpness is one thing, and strength and durability and flexibility is another. The Japanese sword just happens to have all of that all together in one. So can the Japanese sword shave the hair off your arm? Well, yes, it can. Is it as sharp as a razor blade? Yes, it is. But can a razor blade cut through a helmet? No.
The Japanese, being the perfectionists that they are, spent an awful lot of time making it the perfect cutting tool. The curvature on the edge allows you to swing straight and still use a slicing motion. It's what we call differentially tempered, which means the edge is much harder than the back. So the back can act as a shock absorber, but the edge doesn't get soft when you cut it too often. It stays sharp.
Indeed, the edge on a well-crafted katana blade never needs sharpening. How did the katana's makers achieve this deadly and enduring sharpness? There's a clue in what appear to be blemishes on the katana blade's face. Swordsmith K.C. Lund will show the significance of these marks as he fashions a katana using the same process originated a millennium ago by Japanese artisans. His initial steps are much like those followed by European swordsmiths. Lund begins by hammering steel chips together and shaping them into a bar. Then he repeatedly folds the bar in half, hammering and elongating the steel until he's created the katana's basic shape. Now Lund performs a crucial step unique to the Japanese process. He begins to coat the back of the blade in clay. The clay will insulate the underlying steel from the full effects of a subsequent heat treatment. It will alter the microstructure of the steel and harden the blade. The exposed steel will harden completely in order to support a razor-sharp edge. But as steel becomes harder, it becomes more brittle, more like glass.
Even the little pieces of clay will leave a somewhat softer area, The hope is that this is going to prevent any type of cracks that might run down the length of the blade.
Lund now performs the hardening process. First by heating the clay-coated blade to 1500 degrees Fahrenheit. Then plunging it into a cool salt bath. This produces the trademark scars along the blade. And since the leading edge expands more than the trailing edge during the treatment, the blade becomes curved. It all combines to create a durable, deep slicing instrument. But it's the final crucial touches that turn this edge into the world's sharpest sword.
Now that the blade is hardened on the edge, softer on the back, we need to profile this edge and bring it down into a slight convex edge. It'll be done on a water stone, which is the way it's been done for hundreds of years.
In addition to its characteristic hard edge, the convex shape of the katana blade also sets it apart from European models.
It really comes down to blade geometry, and that has a lot to do with the ability of a sword to cut through a target. Usually, your European blade, the body would be like this. You've got a very thin edge. It doesn't have much supporting it. And what that causes is quite a bit of resistance as it cuts through an object. Whereas a Japanese sword, they're fairly thick blades, and they were convex ground. So as they go through a target, the stuff they're cutting tends to peel off. The whole blade isn't dragging through the item it's cutting. Plus, they have a lot of support behind the edge of the blade to give it more strength.
So is the katana truly the sharpest sword?
The proof of that is that Japanese swords haven't changed in their construction for over 1,000 years. If there were any modern technological improvements to be made, steel or anything, it would have been done.
Today, the most vicious enemy any of us attack with a razor-sharp blade might be a common vegetable. But there's no need to carry a 20-plus inch katana blade into the kitchen. Cutco Cutlery of Olean, New York, claims to create the sharpest kitchen knives in the world. It all starts with a steel alloy containing chromium. For the perfect balance of strength, edge retention, and corrosion resistance, the metal will undergo a high-tech heat treatment.
We got the finest steel, but if we don't go through a proper heat treating process, we've wasted all our money. This will just show you here, this is not heat treated. So here's what we would have if we did not heat treat this blade. It would bend in your home, it would not hold an edge.
In the first step of the brutal three-part heat treat process, a conveyor feeds newly stamped unsharpened blank blades through a furnace.
Now we're going to put it in a deep freezer and freeze it to 120 degrees below zero for about 2 hours at temperature and pull it out.
After these two steps, the cold steel blades are far from finished.
What we would have now is a brittle part. And what you see here on the table is that here's some parts that have been heat treated and frozen, but they're very brittle. If I put this in, you can see here that it broke very easily.
To overcome this problem, another furnace warms the steel again.
That will give us a tough part. Very much what we see right here in these knives that have been ground and finished, but you can see how they'll flex.
Now that each blank has just the right steel consistency, it's time to grind their edges. Each blank, now 95 thousandths of an inch thick, passes through an automatic grinder, which tapers its edge to just 18 thousandths of an inch. This is about 5 times as thick as a sheet of paper. But we've only gotten started. Now here comes the process that'll turn these edges into the world's sharpest. Operators manually press each blade, one side at a time, along a powered 4-inch wide moving conveyor belt, with a consistency not unlike sandpaper. In seconds, a barely visible light line appears on the rim. This is called the burr. Need a better look? The honing process grinds down the metal until the two faces meet each other at the edge. Once they do, one side of the metal curls over the other and produces the burr, which is a thin, nearly microscopic wire.
It's just a floppy piece of thread like hanging on the edge, and actually it bends back and forth, so you need to take it off till you get down to the strength of the edge.
If the burr were not removed, the knife would act more like a saw. Polishing erases the burr.
If you use a cloth buff, much as you'd use if you were polishing your car with an automatic buffer, the wheels are turning 3,600 RPM. So when they're turning, they're hard as a rock. What we're actually doing is polishing the edge, which actually buffs away the burr and makes it very smooth, so the edge actually glides through the foods that it's cutting.
Heated, ground, sharpened, and deburred. The cutting edge now measures a super thin 1/10,000th of an inch, 20 times thinner than a human hair. But this minute edge isn't the only measure of a sharp and effective kitchen knife. It must also keep its edge for as long as possible. What good is a knife if it can only slice well through its first pineapple? To prove its knives are superior to other brands, Cutco conducts a Catra test, an industry standard. The test simulates wear on the blade by forcing it through thin cardboard strips filled with fine granules of sand. The test will measure not only the effectiveness of its first slice, but also of its 60th.
One of the important factors that the cutlery industry wants is how sharp is this knife going to be when you buy it? And, of course, the longevity. How long is that knife going to last?
For some perspective, a butter knife takes the stage first. It doesn't exactly make the cut.
Actually, it's supposed to be doing some cutting through on the test media. About all it will do is probably cut butter. It's not going to get through maybe one of our test media after 60 times.
Repeated tests help back up Cutco's claim that it's the sharpest knife you can find in a kitchen drawer.
Out-of-package sharpness will give us an average of approximately 30 cuts. Total card cut after 60 times gives us approximately 400 cuts of this test media.
Over time, however, even what's billed as the world's sharpest kitchen knife inevitably dulls. But the food it's cutting isn't necessarily the reason.
It's other things that the knife comes in contact that does the dulling. China plates or glass cutting boards or very hard other surfaces.
To combat the dulling effect, Cutco manufactures a blade with an unusual edge they call the Double D. Protruding points line the lower lip of the blade and protect the sharp cutting surfaces, which hide in upper U-shaped recesses.
What's going on here is the points are what's touching the glass plate. So what's being dulled are the points, not the upper parts of the edge.
Think these blades are sharp? Chances are you have a very close encounter every morning with a blade over 80 times sharper. Keep that hand steady. The sharpest cutting tool in the world is a diamond blade. Its finest cutting edge can measure less than 10 nanometers across, 5,000 times thinner than a human hair. World's Sharpest will return on Modern Marvels. A century ago, the sharpest edge most men encountered was at their local barber shop. There, skilled professionals gripped blades sharp enough to split hairs, hopefully without cutting flesh. Today, in some barbershops, little has changed. Keeping shaving blades razor sharp is an ongoing challenge, as shaving hair nicks steel and dulls them. But old pros like Damon Zilli have made honing them an art form. He manually grinds the straight razor over a double-sided honing stone to restore the damaged edge.
The black side's more of a coarse side, and the brown side's more of a refined side. It's a little smoother, softer type of stone. So that's what I'm doing right now. Can't see it, but I'm just taking off the microscopic nicks on there.
And just like the cutlery makers at Cutco polish the burr off of their knives, Damon needs to smooth his razor's edge.
The first step right here is I'm going to strop with the canvas. So right now it's just getting rid of the excess metal that was on the edge of my blade right here. So now I'm going to flip it over, and now I'm going to focus on the leather portion of the strop. Basically, it's a little finer finish, and it closes the pores and gaps and nicks on the edge of my razor blade. If I didn't do the stropping, my customer wouldn't get a good shave, period.
Over 200 years ago, the first steel straight razors were so expensive, most men had to visit a professional barber for a close shave.
If I don't use the sharpest blade, he's going to walk out here an unhappy customer.
But beginning in 1904, the safety razor armed us with disposable blades, so sharp and so inexpensive that worldwide we now spend $10 billion every year shaving ourselves at home. On these blades, we find the sharpest steel edges in the world. At this Schick plant in Connecticut, grinding millions of microscopically sharp edges begins with a thin ribbon of steel.
This steel is unique to the manufacturing of razor blades, and what makes it special for that application is the microstructure of the steel. It's made in such a way that we can grind a very fine edge on it.
Each coil contains 2 miles of steel 3/1000ths of an inch thick, enough to produce 80,000 razor blades.
A razor blade is ground with 3 distinct facets or bevels, so it is not a straight edge that leads to the ultimate tip.
A grinder crafts these 3 facets into the steel coil. Textured sandpaper-like grinding wheels mill the front and back of the coil simultaneously.
In the first stage, very coarse wheels are used. These grinding wheels do most of the stock removal. That is to say, bring the blade to the width that you want it. On the second stage, a finer grit wheels is used. In this second bevel, this is the preparation to the third and final stage. The final stage is ground using very fine grit wheels that leave a very smooth and continuous edge on the blade.
Grinders also mill the opposite edge of the coil, resulting in a double-sided sharpened strip. Then, a guillotine chops the steel into individual 1.5-inch long blades.
Here you can see the individual blade with sharp edges both on top and the bottom. Eventually, this blade will be cut in half, and this will be a single edge that will be assembled into a razor or cartridge.
The edges on the world's sharpest razor blades measure just 30 nanometers thick, over 3,000 times thinner than a sheet of paper. But surprisingly, they still aren't good enough to shave with. Why? Because they're not yet strong enough to take on a formidable foe: human hair.
Human hair is in fact very tough. The hardness is really equivalent to copper of the same diameter. You really want the edge of the blade to be as hard as possible, yet as sharp as possible.
As sharp as these blades are, Schick has to fortify them with 2 separate coatings to make them practical. Inside this vacuum chamber, Schick's Quattro blades are coated with the company's hardest available covering, a combination of titanium and man-made diamond. And inside a second chamber, a low-friction polymer film is sprayed onto the cutting edge.
The first coating process basically makes the edge harder, and the second process basically makes the edge slipperier so that it glides through the hairs instead of pulling and tugging at them.
Finally, the blades move to the assembly department. There, a high-speed automated process mounts the blades to plastic components and packages the completed disposable razors. They're now ready to bring a close shave to the masses. Of course, their edges aren't called razor sharp for nothing. Under the unforgiving eye of the microscope, The edge of a paring knife sample looks like a jagged mess compared to a razor blade.
We're only at 150 times magnification. You can clearly see the edge of the knife, but over here on the left, the razor blade is almost invisible at this point. And that's simply because the razor blade tip is so much finer than the knife. This is the sharpest edge you can get on steel.
That may be true, but no steel blade can do the job of these ultra-sharp cutters. Slicing hour after hour through this tough plastic film that will eventually be transformed into your household plastic wrap. Produced by Specialty Blades in Virginia, they may look like ordinary steel, but they're made of zirconia ceramic. Their edges are far more slippery than steel, enabling them to stay razor sharp up to 100 times longer.
The film itself is rubbing against the sides of the ceramic right past the edge. And if you have a material with a low coefficient of friction, the film does not get stretched and you get a better cut. The other thing that makes ceramic good in film slitting is it's a really hard material, so we can put a fine edge on it without getting burrs.
Zirconia ceramic is about 6 times harder than steel, but it's also more brittle.
We never recommend a ceramic blade in a high impact application because the ceramic edge will chip.
Just like the process that sharpens steel razor blades, pairs of grinding wheels inside this housing hone ceramic simultaneously on 2 sides, but with one crucial difference.
The sharpening of ceramic requires the use of diamond grinding wheels and hones. When you get into something as hard as zirconia ceramic, you have to have a grinding wheel that's harder than the material being sharpened. One of the things that surprises a lot of people about these blades is how sharp they are right when they come out of the machine. For example, here's a piece of notebook paper, and this blade will just forever come in and cut little pieces off of it. Try that with your pocket knife sometime and see if it'll work.
Yes, getting through a piece of paper is not so tough with the right blade. But which of the world's sharpest would you need to get through something like a fridge? How about 2 miles worth of overpowering jumbo scissors? The sharpest object ever created is a probing tool for a scanning electron microscope. Its probing needle, made of tungsten, narrows to a tip just 1 atom wide. The world's sharpest will return on Modern Marvels. Meet the BC 1800 XL, manufactured by Vermeer. An 8,700-pound wood-chipping brute, vying for the title of the world's sharpest yard tool. It can clear your backyard of a forest full of fallen trees or overgrown bushes and pulverize it into mulch. This monster devours each mouthful of wood effortlessly, thanks in part to its belly full of ultra-sharp steel alloy knives.
This drum here has 4 knives on it. As I slowly rotate this, you'll see that they're staggered, offset to each other at approximately 90 degrees in relation to the drums. In relation to what we're used to in everyday life, it's probably sharper than any knife that you would find in the average household of America today.
These super sharp edges will make well over 2,000 separate cuts into a 60-foot-long tree trunk as it passes through the chipper. They get a big assist from a 140-horsepower diesel engine.
Velocity is one of the key factors in the chipping process. Without the velocity, we're not going to have the power to impact the wood.
The engine feeds enough power and torque to the drum to rotate it 1,100 times every minute, or over 18 times every second. 2 vertical feed rollers grip the incoming material and guide it toward the 36-inch diameter rotating drum. As each knife mounted on the drum surface impacts the wood, it snips off a chip when it reaches a base-mounted shear bar. The distance between the shear bar and the cutting knives determines the chip size.
There's paddles. What that does is creates airflow. We need a tremendous amount of airflow to create the discharge and keep the chips moving out.
After about 40 hours of this punishing labor, the knive's edges begin to dull.
The machine isn't designed to hammer or pound through the logs. It's designed to cut through, and that's where you need a very sharp, consistent tool to do that.
Restoring the cutting edge requires some expert treatment.
This machine sharpens blades, which I have right here, and this will be in here, like so. There's a stone that rotates clockwise, and it moves along, and it just sharpens just like that.
The sharpener grinds away at the blade and refreshes its 30-degree angle and restores its pristine edge. Brush chippers like the BC 1800 XL can plow through this mass of vegetation as fast as you can feed it. But another set of powered blade cutters redefines the notion of ultra sharpness by cutting not just through wood, but anything else. And we mean anything. Enter the almighty Primax, manufactured by SSI Shredding Systems of Oregon. The Primax was called on to clear the debris from New Orleans after Hurricane Katrina. It's the perfect tool for demolition sites and huge recycling projects. It can reduce unwanted bulk to a fraction of its original mass.
Well, here's what's left over from the sofa. You have a chunk of the fabric, piece of the back cushion. Here's the foam that you actually would sit on, and a big chunk of the wood from the bottom of it. This machine will just process it all.
Inside the Primax's gaping mouth, two parallel shafts each hold 6 3-inch thick steel circular cutters, rimmed with pointed hooks.
These things are really designed to shred almost anything. These cutters have a piercing point on them. They literally pierce the material, and then the material is brought down into the root of the cutter, where the actual torque is transferred into it, and then it uses just brute force to break the material.
That brute force is supplied by a 700 horsepower diesel engine. It enables the shredder to digest up to 150 tons of material every hour.
The machine's really just designed to take the airspace out of the material, break it down, and prepare it for either transportation or recycling operations.
But some recycling operations, like those processing rubber tires and plastic products, require shredders that can break down material into much smaller pieces. This makes it easier to process the material into something new. The answer is a shredder like this one, with blades positioned much closer together than those of the Primax.
You have two cutters here, and in between them is a surface that's just exactly like between the two surfaces of the scissors here. What we have is a whole bunch of what I call shear pairs, which are just exactly like scissors, and the shafts are turning, and they force those scissors to come together right there at the joint, and material falling in there. It's just like having a whole line of scissors and a whole bunch of people just snip, 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 all simultaneously, doing that as it goes across. One of the things that can happen is when you're cutting paper, you're sort of keeping the two halves of the blade tight together, and then they shear the paper quite nicely, and you get a nice clean cut. Well, what can also happen is if you turn the scissors sideways, you can get a situation where the paper is laying right between the cutters, right down the middle, and it's not sheared at all. Well, you can have exactly the same situation here on this shredder. Unless we keep that stuff tight, all of these cutters and spacers very tight, we're trying to go to about 10,000ths of an inch gap between each cutter so that we get a good shearing action at each joint.
An effective shearing action without a sharp edge would render these shredders as little more than giant mechanized kids' safety scissors. So to ensure those sharp edges make the grade, SSI's engineers produce them using a meticulous hardening process.
We take a hand grinder and grind a weld prep or a beveled 45-degree angle along the whole edge. And what we're going to do is fill that area in with weld, and after it cools and settles, it becomes incredibly hard.
Next, workers grind down the irregular welded sides of each blade. Then, an automatic grinder flattens and smooths the face.
And this flat combined with this flat makes for this edge now to be really, really, really sharp. These really tight tolerances in the super flat blade gives us that sort of shearing action that we really like when the blades are really close together. The closer they are and the sharper they are, the better it does for shearing.
The blades team together to create 15,000 times the shearing force of a single pair of scissors.
We've got about 35 or 40 cutters in this machine, so about 4,000 inches of scissor action. And then if you look at this machine turning at about 20 RPM, we have about a mile of scissor length that we're cutting per minute.
By adding a second pair of bladed shafts and an underlying screen, leftover shreds fall out as little more than particles. Not every tool vying for the title of world's sharpest has a solid edge. Imagine a razor-sharp wonder that captures lightning in a bottle. The largest shredder ever built by SSI Shredding Systems shears with 60,000 times the force of a standard pair of scissors. The world's sharpest will return on Modern Marvels. The world's sharpest cutters don't have to be intricately hardened and honed blades. Instead, they can be made from something that's not even solid. The cutting experts at Southern California's Hansen Steel Services carve through solid steel plate with a laser, an intense beam of microscopically focused light. It's the most effective tool for making exacting cuts in steel, less than 1 inch thick. The sharpest industrial metal cut made by a laser can measure just 4/1000ths of an inch across, about as thin as a sheet of paper. Chances are that a laser has cut thousands of common steel parts that surround you every day. From the components in your DVD player, to the stainless steel skins of modern kitchen appliances, to the sprockets and gears in your fishing reel. Before industrial lasers came into their own in the 1980s, precision shaping steel relied on slower and less cost-effective methods. Parts had to be punched out by press or machined with skillful care. A laser generates its cutting beam by converting gases into surgically precise energy. A resonator within the laser housing channels a direct current into a glass tube containing gas, like carbon dioxide. The current excites the gas, which emits photons of light.
It'll actually start off when it comes out of the resonator at about approximately inch and a half. And as it comes down through the laser head, it hits a focusing lens and it brings it down into such a fine point that you can almost not see.
The naked eye sees only the warm glow of the laser impacting and melting through the steel. The laser light itself is nearly invisible because it differs greatly from visible light. Visible light contains a myriad of wavelengths and is ultimately scattered and weak. Laser light consists of just a single wavelength. For this reason, it remains concentrated and powerful. Passing the light from a 100-watt bulb through the same laser cutting mechanism would only focus the beam to a minimum area of 4/10 of an inch and an energy level over 4,000 times weaker than that of the laser.
This one right here is a 1,700-watt laser. It's approximately 20 million watts per square centimeter is what it's measured as. Whereas if you were to measure like a soldering iron, would be about maybe 100 watts per square centimeter.
The most powerful lasers can slice through steel up to 1.25 inches thick at nearly 60 inches per minute.
All this is really a sharp cut. What happens is that the edges are so straight with the laser beam. On the bottom side, you can see if you feel the bottom, you have no burr, there's no dross, it's real smooth. It's the same as basically the top side of the cut. Basically, if you were to take and stand this part straight up and down, it'll stay just like it is.
As sharp and precise as lasers are, however, they're not brawny enough to cut efficiently through steel more than an inch thick, like some of that found in the frame of your car. To tackle that type of job, you need this otherworldly cutting power: plasma. Plasma is gas superheated to the fourth state of matter. It's found burning on the sun or flashing in lightning.
This right now is cutting half-inch plate. It's cutting about 75 inches a minute, and it can do up to about 2.5-inch thick plate.
The ultra-thin ray of plasma is capable of a blasting incision just 4 times thicker than a human hair. The power of the incision comes from plasma cutters, hovering over the steel plate surface. To create this intensely sharp beam, pressurized gas, like oxygen, is forced through a narrow cavity. A negatively charged electrode positioned in the cavity center creates a spark when the plasma cutter nozzle touches the surface of the positively charged steel plate. At the atomic level, the extreme heat strips free the gas's electrons. This ionizes the gas molecules, creating electrically conductive plasma.
As it comes out of the nozzle, it cuts at about 25,000 to 30,000 degrees.
The plasma is also flowing at up to 22,000 feet per second. That's fast enough to zip from New York to Los Angeles in a little over 10 minutes.
So what you're seeing there with the sparks that come out is essentially because the material has nowhere else to go. So until it starts cutting, it basically shoots the sparks back out of the top.
But once the plasma fully penetrates, the computer-controlled cutters have no trouble crafting any shapes fancied by its operators. Specialized ultraviolet lasers, like those used for LASIK eye surgery, can create incisions measuring just 250 nanometers, 200 times thinner than a human hair. The world's sharpest will return on Modern Marvels, here on the History Channel. While man has been honing cutting edges for thousands of years, Mother Nature has been perfecting hers for millions. Understanding this, researchers at the University of San Diego are seeking to mimic nature's sharpest creations and to engineer ever sharper technologies in the future. They're paying particular attention to the notion that in nature, harder doesn't always mean sharper.
It's very interesting to see that weak materials, soft materials, when put into a really optimized structure, can cut through materials that are sometimes much harder or tougher.
Common grass filled with cellulose is a perfect example.
You wouldn't imagine that something as simple as a blade of grass could be a sharp cutting edge. Well, in fact, it really can. I mean, if you think about it, a blade of grass is made up from very weak materials, but it can oftentimes leave you with scars and cuts that you never imagined possible. The microstructure is what creates that cutting edge.
An optimized microstructure also holds the key to how the mosquito, a creature that's killed more humans than war, is able to puncture tough hides and flesh with its needle stinger proboscis.
If you think about a mosquito, the needle has to actually enter your skin and be able to retract out very quickly after it's finished and just do this sort of painlessly, right? So it can fly away without you even noticing.
The tip of the needle, it has some serrations. And these small serrations cut through the tissue, okay? And it doesn't compress the tissue.
This puncturing ability is different than a conventional syringe needle, which terminates at an angled point, like a sharp-ended straw. Japanese researchers are mimicking the mosquito to develop a pain-free syringe. Just as the mosquito's proboscis tip is lined with serrations, so too is the prototype syringe. Also, in contrast to a conventional shape, the needle is thinner and shorter to reduce friction and skin contact. The rat, nature's quintessential urban pest, has also provided scientists a model to craft a cutting blade that never dulls.
As we know, rats will chew through electrical wire, through drywall, through everything that they find. And that's also a way in which they keep their teeth sharp. What we have here is a skull of a rat with the incisors, and the screen here shows those 4 rat teeth. This is the upper incisor, and this is the lower teeth. The external layer has the hard enamel, and here is the inside, that is the softer dentine.
As a rat chews and bites, the dentine wears away faster than the enamel. This preserves the incisor's sharp, pointed shape.
If it was a uniform material, we will end up with teeth that would be completely flat.
Using the rat's self-sharpening incisors as a guide, researchers in Germany have developed so-called self-sharpening milling blades. Emulating the rat tooth's hard enamel and soft dentine combination, the milling blades consist of a hard ceramic layered over a softer tungsten carbide core. Designed to shred paper, the blades rotate around a vertical axis. The softer core wears away more quickly, allowing the blade to retain its sharp shape. Perhaps even more notoriously sharp than rat's teeth are those of the ferocious piranha. Its mouth full of sharp daggers slice through flesh and bone with great ease. But surprisingly, it has relatively weak jaw muscles. The piranha's secret? Its perfectly efficient jawline geography. Each triangular tooth angles to an unusually sharp 45-degree point. Additionally, the piranha's underbite leaves virtually no space between the upper and lower teeth when they chomp down. And studying this nasty dental work under a microscope reveals a surprising detail.
If you look in the scanning electron microscope, we were able to identify very, very small serrations.
The jagged edge of each tooth eases the piranha's bite into its prey, minimizing the amount of force needed for penetration.
The fact that the teeth are so well designed leads us to believe that we can create scissors that use the same angles and the same configuration of the piranha.
Imitating the tight fit of the piranha's bite, the proposed scissors would be lined with jagged edges. Additionally, each edge would also contain tiny serrations, so that every snip could potentially cut meat, bone, or leather as easily as conventional scissors cut paper.
What nature provides is this inspiration. We look at nature and, aha, that's how the rat structures his or her teeth. So can I use this concept and apply it to a sharp cutting edge?
We can take our new materials, our hard materials like titanium and different plastics and things like this, and apply those lessons from nature and create things that are beyond your wildest imagination.
We're immersed in a world of razor cuts and prickly points. And if imitation is the sincerest form of flattery, science will continue complimenting Mother Nature in the never-ending search for the next world's sharpest.